Here we are showcasing one of our innovative solution, derived from extracting value out of data, using machine learning techniques. A case in point, was to detect leaks in pipelines carrying mining waste over a length of 4 miles. The project was developed in 2 stages, mathematical modeling of the pipeline system and the implementation of the machine learning techniques for the leak detection system to work. The mathematical modeling of the system was based on the energy conservation principle, considering variables as pressure, fluid density, height and flow velocity. The gravity acceleration was considered, as well as the cargo loss, which is associated with the fluid's energy drop due to its contact with the pipe's inner wall. Once the modeling was done, the energy is measured at a point of the pipe, considering energy as pressure over fluid density, then machine learning techniques were used to predict the energy at another point, based on that measurement. After the model was trained, tests were made to define what would be the line between a simple system modeling error and a real difference meant a leak in the pipeline. The result was a robust system, with leak detection accuracy resulting in only 3 to 5 false alarms each month, saving in manual inspection on a recurring basis. This innovative prediction system was successfully implemented in 3 different pipelines.
This video illustrates how we used an open-source data analytics and reporting software platform for the pipeline leak prediction. Both the historical and streaming data coming from the various sensors that relay pressure, density, airflow, mass and such are stored in a database. Our custom data logic and machine learning models are built into several connected workflow nodes and executed in sequence. The anomalies in the received data points seen over a certain period of time is analyzed to identify a concern for the leak. That transient duration over a defined range, where anomalies are seen and seem to be stable, indicates a possible leak. On such data points, alarms are sent to an OPC server and visualized to take control actions such as calling for a manual inspection. For the paradigm shift, moving from process-driven manufacturing to data-driven manufacturing, industrial equipment monitoring is an important and critical task that plant and operations managers pay attention to gain productivity insights. Using an IoT platform, it makes it possible to collect, organize, report, and respond to data from systems to create more value for our customers as well as to equipment providers. This video shows how telemetry data monitoring is done in a renewable energy space. Often, when we talk about renewable energy, the term CHP, the combined heat and power, come up for evaluation. It is very important to monitor and measure how well the OEE of the CHP engine is, how well the energy balance is between electrical and thermal energies produced, what is the waste that escapes to atmosphere, what are the environmental implications in terms of EPA regulations against carbon monoxide emissions, methane levels and such. This video shows few CHP engines that are deployed in several farm areas taking either biogas or natural gas as fuel. Dashboard shows how those streaming telemetry data coming from the generator and the CHP engines are collected, monitored and visualized.
Here is our innovative experience that we created to take accurate volume measurements of an hazardous pile of fertilizers in an indoor warehouse. Our solution involved building and executing an autonomous drone flight path to learn the indoor layout of the warehouse, with collision avoidance between struts and beams in place, capture images of the pile, and offline analyze the point cloud data to get the accurate volume information. Drone structure was modified and equipped with additional sensors such as LiDAR, UWB sensors for flight trajectory. The existing effort in getting the volume information was a manual process where a personnel have to climb up the hazardous pile and take the measurement. This was in 24 hours of effort, which with innovative drone idea brought down to 40 seconds. This innovative solution is highly scalable and deployable in any indoor warehouse once the layout is learned. The offline analysis of point cloud data is customizable for the situation in question, such as measurement of either volume or number of pieces of equipment, etc.
Hi, I'm Sophie, Stefanini's omni-channel virtual assistant. Today, I'm presenting the ERA Logistics Integrated System, from conception to reality. The system's goal is to optimize loading and unloading operations through the real-time control and monitoring of trucks in the Yara industrial area according to a planned production sequencing. The truck driver heads to the reception and requests his access to the plant through the self-service units. He receives an RFID device that will track him throughout the plant. Monitors will show the loading forecast for each truck. Access to the plant is controlled automatically through the access module. The truck driver parks and waits for the call to load. The audio module makes the call according to the program sequence. Once the load is authorized, the driver proceeds to the weigh-in. Logistics dynamics are monitored remotely directly from the operations center. It is possible to act over the system components individually and make changes in real time in the flow. The weigh-in is performed one more time for the load calculation. The driver uses the self-service module to return the tag and issue the invoice. The access module enables the exit through a printed code in the invoice.